test tomorrow over mostly Chapter 7 and then all of Chapter 8. We started on Section 2 out of Chapter 7 way back, as before spring break, so that makes this one seem even longer than it is. It's long enough by itself, but then have a week break in there. But we'll go through step by step and talk about or remind you about what we covered way back then. But first of all, there are only 13 problems in the entire test. The problems are a little longer than just your basic problems, so each problem will be worth 5 points. So that'll be a total of 65 points, and then I'll figure a percent from that for your grade. But each one will be worth a little bit more percentage-wise than what we've done before. Okay. Now, in 7.2, we looked at a couple different types of applications. And first of all, we looked at higher order derivatives. Order. Like your second derivative, third derivative, fourth derivative, etc. And as we've moved through the chapter, we've seen some uses for, well, at least the second derivative. We don't see a lot of uses for the third and fourth derivatives, but we can at least calculate those, and we have notation for third and fourth derivatives. So that's more recognize the notation, whether it's F triple primed or, well, the primes, we kind of get too many prime markings after that, so a lot of times we'll write it as third derivative with parentheses around that 3, or a little more formal notation, d3y by dx cubed. Okay, these are all notation for third derivative. Fourth derivative, you'd have a 4 in there. Eighth derivative, you'd have an 8 in there. I'm not sure we'll go quite that high, but and some of these you may end up starting with, here is the second derivative, what would the fifth derivative be, or something like that. So be able to find higher order derivatives. And in that section, we also looked at finding a linear approximation and really the linear approximation is, the basic idea is use the equation of the tangent line and find a value close on the tangent line to the actual function value. Like a square root of 10, well, we know square root of 9 is 3, at least I hope you know that. So we kind of make it a nice value like A equals 9 or C equals 9, whatever letter they use. And then we are looking for when it's 10, so delta x would be 1, the 10 minus the 9. And then go through, you'd have to find your derivative. Let's see, the shortcut, going through all the procedures and stuff, the shortcut for it would be I'll just use f of a and then plus f primed of a times delta x. So to approximate square root of 10, well, we choose a equals 9. And then plus f primed of 9 times 10 minus 9. Then your delta x will end up equaling 1. And let's see, it'd be square root of 9 would be 3. F primed of 9, well, first f primed of x, got to take the derivative, ends up with 1 over 2 square root of x, I think. So then square root of x, square root of 9 would be 3. So, and then times your 2. F primed of 9 would be 1/6. And then times the 1. 1/6 plus f of 9, 1/6 plus square root of 9 would give you your approximation, linear approximation of square root of 10. So kind of, it looks a lot more complicated than it is once you kind of understand it. It's just the equation of the tangent line and then use it with nice numbers to approximate your ugly number, square root of 10. That was our first section in chapter 7 that we looked at here. Again, 7.2. Also 7.2, the last subsection, dealt with one more application, approximating the solution to an equation using Newton's method. And that, again, the theory behind it, we're using the equation of the tangent line, but the nice formula that you'll need to be remembering, the x value that we'll say is approximately the solution. Well, that x value is going to be the previous x value minus, let's see, f of x sub n divided by f primed of x sub n. So there again, a little formula that you'll need to know, and you can, the tricky part here is figuring out, okay, where do we need to start? A lot of times we can look at 0, but sometimes 1 would be a better place to start, or even 2, maybe even -1. Depends on the function, depends on what function values we get with those. But start, let's say if we start with 1, we'd have 1 minus f of 1 over f primed of 1, and then from there use that result as your next x value, and eventually you'll get close enough. I will have you continue this process as we did on the worksheet until 2 successive applications differ by 0.001. So you've got to do a few operations on it, but it's not like you're going to have to do 20 different steps to this one. More like probably 3 or 4 steps to get those 2 successive choices close enough, close to your 0.001. Okay, questions on that? After kind of those specific applications, we looked at a more general, more useful application in the real-world sense, optimization. And again, it's finding your maximum and or minimum value given a certain situation. Most of the time with these problems, you'll have a function, or actually you'll have an equation that you're asked to find either the maximum or minimum of, and then another particular situation that you know that will give you a relationship. Maybe it's trying to maximize the area of some rectangle. Well, area of a rectangle is length times width, or a lot of times we use x times y on that. And then the other situation, we know how much, if we're trying to fence in this rectangle, we know how much fence we have, so we have 2x plus 2y equals the 100, if it's 100 feet of fence or something like that. Now there may be some different stipulations than just going around the perimeter. Maybe it's we have a rectangle and we want to cut the rectangle in half with a third. Maybe we make two different rectangular pins here, and so if this is x and this is y, still the area is going to be x times y, but then our relationship, our fence, we'd have 2 lengths of x, but we'd have how many y? We'd have to use the fence for 3 lengths of y in this situation. And again, whatever amount of fence, 100 feet of fence, 250 feet of fence, whatever that is. Well, that allows us then to solve this equation for one of the variables substituted into the original, and that creates a function of one variable. In this case, it might be easier to solve for x, actually. Divide by 2, and we'd have x equals 50 minus 3 halves y. Plug that in there, and then your area turns out to be a function of y. You have x times y, and of course, to make this as easy as we can, multiply the y through 50y minus 3 halves y squared, and then it's a matter of finding the maximum of that function. Take the derivative, set it equal to 0, and solve for y. So the hardest part about these tend to be setting up your information, finding the function we're trying to maximize or minimize with the given information. So again, most always will have some form of equation, formula that we're trying to maximize or minimize, but in 2 variables, and then some other information like this that we can solve for one of the variables, substitute it in, and make it a function of just one variable. Yeah.
So, if I remember right, I remember that we would take the derivative of one of the...
Okay, then, yeah, once you get to this point, which is really just the algebra part, now you're ready for some calculus. Take the derivative of this, set it equal to 0, and as we started using some different terminology in Chapter 8 with the graphs, what we're doing right here would actually be just finding your critical points. Okay, so once you find the function, then take the derivative, set it equal to 0, and then figure out does that represent where it's going to be the maximum or the minimum? Most of the time, this right here answers the question, but we've got to use the information given to us. Okay. Other questions on that part?
So a problem like that, they're asking for the dimensions of X and Y?
A problem like this may ask for what are the dimensions. So the answer would be both the X and the Y in terms of feet. Don't forget your units on there. Or it may say what is the largest area that could be enclosed by this. So with this situation, and the answer there would be the actual area, X times Y, whatever that would come out to be, and then square feet for your units. So in these optimization problems, you may be asked a couple different types of questions. The procedure is the same, but it's a matter of recognizing, well, are we needing length and width, or are we needing the actual area? And later on, we looked at some other types of optimization, like the volume. What's the largest volume of a box created by different situations? Or maybe it's find the minimum surface area to create a box, or maybe a right circular cylinder given a certain volume. So there, kind of, instead of being given perimeter, or in those cases, instead of being given area and asked to find volume, given surface area and asked to find maximum volume, maybe it's flipped around where we're given the volume and asked to find the minimum surface area. So as we kind of expand out to the three-dimensional objects, boxes, right circular cylinders, those types of things. Now, I will not give you like the formulas for the obvious things. Area of a rectangle, you need to know that. You better know that by now. And perimeter, but for a box, volume is length times width times height. Again, you should know that. Volume of a right circular cylinder, you should know that one as well. Pi r squared h. So some of the things, some of the more common ones you better know. But if it's like one of these, we had an octagon. I'm not going to expect you to know the area of an octagon. If it's a kind of one of those weirder formulas, not so common, I will either give you the formula for that, or it's not going to be on the test. But for the basic ones, you need to know, up through and including your right circular cylinder. Okay, but for a cone or a pyramid or something like that, I would give you the formula if that's necessary. Okay, but optimization, lots and lots of different types of problems that we looked at. But again, the basic idea on those: find your formula for what you're trying to maximize or minimize. Then with the other information given, you'll be able to get a relationship between two of your unknowns, solve that, plug it into the formula, and eventually you'll get down to a function of just one variable, and then you start doing the calculus, find your critical numbers, and where is it a maximum or minimum. Okay? So yeah, that one can take many different forms, but the basic idea is just that. Okay. Another application that we looked at a lot were the related rates. how fast one quantity is changing with respect to time compared to how fast another quantity is changing with respect to time. And once again, with those, just lots and lots of different situations. The main idea there, let's say we have an airplane flying at some fixed altitude. Well, this we know would be changing if the airplane continues to fly. And this would be changing, but your fixed altitude, maybe it's at, what would be maybe at a cruising altitude of 20,000 feet. Okay. Your relationship between the quantities, triangle here, we would have x squared plus the 20,000 squared equals s squared. And maybe we're wanting to find out how fast the distance between this point and the airplane is changing when the airplane horizontally is a certain distance, x equals maybe 5,000 feet. Okay. So, and again, lots and lots of different possible questions from that. The main thing, get your relationship. Now, this is in general. Don't plug in the 5,000 for x when you're generalizing this. Okay, we do this first. Then when we take the derivative with respect to time, we would have 2x dx by dt plus, well, derivative of that constant is going to be 0, but then derivative of s squared would be 2s times ds by dt. And then you could kind of fill in what you don't know. You would be able to find s at that particular point, plug in your 5,000, okay, and then plug in x, plug in s. We would also be given how fast the plane would be going. So dx by dt would be given velocity of the plane or ground speed of the plane. Okay. And that way we could calculate what ds by dt is at that particular time. So just lots and lots of possible types of problems. Again, the generalization, how do we solve something like this? We have to find an equation representing the quantities involved. Most likely we'll be taking the derivative with respect to time of that equation, and then we can start plugging in the known values. Sometimes, like in this case, we'd have to calculate a value from the relationship we already have. When x is 5,000, we could calculate what s is. So, lots and lots of details on these, but same basic procedure for your related rates. Questions there? Now, once we got past the applications, we got into Chapter 8, dealt more with graphing and all of the tremendous detail that goes into the graphing. First, we looked at critical points, which again we'd actually been doing with the applications, we just hadn't called them that yet, and then finding where the maximums and minimums were. Critical points, remember, could be where the derivative is equal to 0, Or, oops, that's not what I wanted. Where the derivative is undefined. We did have a few situations where it ended up undefined, but most of the time it was where the derivative was 0. And through that we could find where the maximums were, minimums, relative maximums, relative minimums, or local max, local min. Can't remember exactly which term the videos used, but sometimes we're also restricted on a domain. So in that case, we could find absolute maximums and minimums. And say, well, we'll just make it a real easy one. X squared from -2 to 3. Well, the closed interval is saying x equals -2 is a possibility, x equals 3 is a possibility, but anything outside of that interval is not included. And of course, graphically, you should be able to figure this one out pretty easily if I could graph right. This would be the graph, and our minimum would actually be 0 at x equals 0. And that shows the possibility of either a minimum or a maximum being at a critical point. That would be where the derivative equals 0 in this case. And the maximum for this function on this restriction would be 9, which would be the end point where x equals 3. But what we'd have to do, we could show x equals 0 is a critical point, and then we'd have to calculate function value at both endpoints as well as the critical point in the interval. That's key as well. Sometimes the critical points are not in the interval. If this would have been from 1 to 3, then our critical point would not be used because it does not fit in the interval. But -2 to 3, the critical point does fit in the interval. So calculating, we find 0 would be the minimum and 9 would be the maximum. Okay, so critical points and endpoints are possibilities for maximums and minimums, absolute maximums and absolute minimums. Okay. Now, we next talked about where a function would be increasing, where a function would be decreasing. And what did we find where the function was increasing? What characteristic would be increasing part? Okay, where the first derivative is positive or greater than 0. And decreasing would be where the first derivative is negative. So we had several problems, find the intervals of increasing and decreasing. And again, the basic problem there, find your critical points first, and then find where that would be where the derivatives are 0 or undefined, and set up your table and figure out where derivative is positive, where it's negative, and so on. Question?
Might be a dumb question, but we're going to have to actually make our own graphs? Or?
That actually is not a dumb question at all. let's hang on to that one, and we'll answer that question here in just a second. Now, increasing and decreasing is one major part of graphing, as James asked about. Another major part of graphing is concavity. And to find out whether the curve is concave up or concave down, what do we look at there? Concave up curve would have second derivative being positive, and concave down is where the second derivative would be negative. And there's some of the problems we did. We graphed in great detail, find all the critical points, find intervals of increasing, decreasing, find where it's concave up, concave down, and then I would have you sketch the graph in detail. Now on the test, I'm not going to have you do all of that in one problem. One problem on the test might be find where this function is increasing and decreasing. Another problem, where is it concave up, where is it concave down? So you'll be doing all of those things, but not as just one single problem, graph this in detail, showing all these different things. I guess I could put one of those on there and count it for 3 different problems, but it's a little bit easier and better for me to see, do you know increasing and decreasing? Do you know concavity and stuff like that? So no, there won't be any, here's a function, do everything you can to it and graph it, but it'll be more, here's one part of it, here's another part, and so on. Okay. So now, that being said, I may have some problems on there. Given certain characteristics, sketch a graph of a function that fits those characteristics. So maybe given f prime of x is positive for x being greater than 2 and negative for x being less than 2. Well, sketch a graph that fits that characteristic or those characteristics. I'll probably have a few more characteristics on there, but something like this, where f primed is positive, it's got to be increasing function. Where f primed is negative, it's got to be decreasing. So something like this, oops. Well, it meant to draw a parabola there, but that would fit those characteristics. There's a lot of different functions that would fit those characteristics, but again, I'll have a few more details listed out. Yeah.
For the concave up and concave down, you set the second derivative to 0.
Right. Concave up and concave down, where that changes would be where the second derivative equals 0.
And
So
on like the normal scene, if it's going up or down,
increasing or decreasing.
set like a point before, like the one that's
Right.
before 0,
Right.
or when it equals 0 after.
Right.
For both of them.
Yep. So yeah, both increasing and decreasing and concavity, once you've found where the first derivative equals 0 or the second derivative equals 0, then set up your number line and test a number on either side of them. Yep. And that way you can see intervals of increasing and decreasing for the first derivative, or concave up, concave down for the second derivative. Okay. Let's see. So some kind of, here's a few characteristics about a function, sketch a graph. That could be problems on the test, but not like the graphing in detail. Here's x cubed minus 3x squared minus 9x plus 8. Graph it in detail. I won't have you do those on the test. Which the last several worksheets, most of them were, here's a bunch of functions, graph them in detail. But the little parts with those, the increasing, decreasing, concave up, concave down, also where's the maximum, where's the minimum, okay. Those types of problems will be on there, as well as one more type of problem. We looked at asymptotes. Rational functions have asymptotes. So find all asymptotes for a particular function. Vertical asymptotes would be found how?
When you try to factor out the function,
Okay.
and then cancel,
Right.
then what's left of it?
Right. Simplify the function first. It's not, most students would look at this and say anywhere the denominator is 0. Not necessarily. If we have, say, the numerator factors into this and the denominator factors into this, well, some students would look at this and say x equals 1 and x equals 2 would be your vertical asymptotes. Not quite. X equals 1, we would actually end up with a hole in the graph, like one of the last worksheets we looked at. Vertical asymptote here would only be x equals 2, because that's the place where the denominator would be 0 after we simplified it. Okay. Horizontal asymptotes, well, that really depends on what the comparing the numerator and denominator. If the denominator is a larger degree than the numerator, then we would have y equals 0. Or usually I say numerator has a less degree than the denominator. If they are equal, meaning the degree, not the function itself, but if we have a x squared in the top and x squared in the bottom, like this one would be, then it'd be the coefficients of your first terms. In the case we looked at here, it would just be 1 over 1. Multiply it out and we'd have an x squared in the top and x squared in the bottom. So y equals 1 would be the horizontal asymptote. And then Friday we did a special in-class activity that goes beyond what we'll test on. I'm not going to ask you for any oblique asymptotes, but that would happen if the numerator had a higher degree than the denominator. So for the test, just worry about vertical and horizontal asymptotes. Okay. So again, lots and lots of different things to deal with in this unit. What makes it so hard is the first part was so long ago. Not just because the unit's so long, but also that 1 week break of spring break. But a lot of looking back and seeing what we've done from the very beginning, 7.2 up to and through chapter 8. So, and tomorrow, if you want to start early, I'll be in here 9:30. So if you want to come in at 10, get started, or even 10:30 and stay late, that's fine. So we will see you tomorrow.